Okay, in this lesson we are going to be covering 6.1 circular motion. This will be part 1 of 3 parts. So the first slide that I always like to start with is this one right here, where you can see the formulas that were in your data booklet. So the formula booklet that you received at the beginning of the year and the one that we've been using throughout this entire course, make sure that is in front of you throughout this lesson, so that you can constantly refer back to the formulas which are being covered. Okay, so in the data booklet, since this is section 6.1, you're going to look for 6.1 in the booklet. Okay, all the formulas are going to be there. Some of which will be covered today, the rest which will be covered in the other 2 parts. Okay. So I'm going to go ahead and move through these slides. Please look through them at your own leisure. This first slide with the animation on, we're going to skip, okay? We're going to address these issues in a lot more detail come the time in the slides. Okay. All right, uniform circular motion. We've discussed uniform circular motion in the last topic. First things first, when you see the word uniform in front of something, that means constant, not changing. Circular motion. Okay, so we investigated this last time. In order for an object to be moving in a circle, that means it has to be traveling at constant speed. Okay, if it's not traveling at constant speed, it would have to be moving in an ellipse. Okay, so hence you're moving at a constant speed. Now, circular motion does not mean you have to travel in a complete circle. You can travel along an arc. You can travel 90 degrees of a circle, or any other angle measurement of a circle. And we will look at that later on when we study arc length. Okay, so in the bottom right here, we've got a bit of an animation. We've got an object that is going to start moving around in a circular motion. Now, the velocity of that object, you can see here, is given by the red vector, and r, the blue vector, that's the distance between the center of the circular motion and the object which is undergoing the circular motion. Now, from what we saw last unit, circular motion can be anything like the Earth orbiting around the sun. It can be a ball being swung, which is attached to a string, swung in a circle above your head. It can be a charged particle entering a magnetic field, which experiences a magnetic force. It can be a car going around a turn as it enters the highway. That's static friction. There are so many examples of this kind of center-pointing force. And if you remember, it was called centripetal force. We'll get to that later on in the slides as well. What I'm trying to get at here is the center-pointing force is parallel to r, and that is perpendicular at 90 degrees to the velocity. Okay, now this object is going to be moving in a circle. What we notice is that the velocity is always tangent to the circle. What that means is every single point in time that elapses, the direction of that velocity vector is changing. Now, the word I just used there, vector, we have to remind ourselves of a couple of things. A vector is a quantity that has magnitude and it has direction. Now, for velocity, we know that when velocity changes with respect to time, you have acceleration. Right? Delta V over delta T. Time is going to elapse anyways. If your velocity changes, that means you're accelerating. Now, since velocity is a vector, in order for the velocity to change, either the magnitude changes, the direction changes, or both of them change. Okay? So most of the examples, and what we have been primarily focusing on so far, are the cases where the magnitude has been changing. We've been considering linear acceleration. The car is speeding up as the light turns green, or it's slowing down as the light turns red. Okay, so we're going to be looking at that case, and we've looked at that case so far, I apologize. right now we're going to see the case where the direction's constantly changing, but the magnitude stays the same. Hence, constant speed, uniform circular motion. Okay? We can see in this picture the object is maintaining its speed, but the direction keeps changing, given by the tangent to the circle. It keeps changing its direction. Okay? So that's what's given on the slides here, everything that I've just explained. If you need to pause the video and read through the slides, feel free to do so. Okay. Now, what you saw last unit, since we had to introduce this concept of circular motion, centripetal acceleration, centripetal force, a little bit suddenly, since it was necessary for the study of magnetic forces and magnetic fields, we didn't really derive or explain why the centripetal force points toward the center of the circle. Okay, so we're going to see that here. If you have an object moving in a circle, what you can do to figure out the direction of the acceleration is pick 2 points in time, any 2 points in time. Okay, but usually you're going to pick 2 points in time that are very close to each other. Okay, so here's the object at one snapshot in time. At a later point in time, it's up here. Okay, and you can see the velocity has changed direction. So if we're going here counterclockwise, that means here on the right, that's the initial position. Here on the left, that's the final position. So V1, V2, you can call it U and V, V initial, V final, whatever you like. One's initial and one's final, okay? So V1 and V2. Now, my definition for acceleration is delta V over delta T. Delta means change, final minus initial. So delta V I can replace with V2 minus V1. Now, we were always taught how to add vectors. And you would have seen this already in physics. You were introduced to this in grade 11 physics. We know how to take care of this kind of a process. If you're subtracting vectors, you can simply assume you are adding the negative vector. So instead of V2 minus V1, you would have V2 plus negative V1. Now, if you look at that, you might say, well, that looks almost the same. And you're right. But the way in which we approach it is going to be a little different. These are vectors represented by those red arrows on the PowerPoint slide. So V2 is V2. It has a certain magnitude. It has a certain direction. You can see that in the picture. If I want to add on to that negative V1, well, I have to know what negative V1 looks like. I know what V1 looks like. It has this direction and it has that magnitude. But if I want to know negative V1, well, we are now talking about the concept of negative vectors. And if you remember our discussion from grade 11, it's been a while, but if you recall, negative vector means same magnitude, opposite direction. So negative V1, opposite direction of V1, same magnitude, same length. Okay, so that's what's being shown on the slides here too, but in a slightly different way. Okay, so we have V2, V1 extracted from the grid there. Now that green arrow that you're seeing, that is negative V1. Notice that it is exactly the same length as V1, but it is anti-parallel. That means it's parallel and it's going in the opposite direction to V1. Now, when you add vectors like we're doing here, V2 plus negative V1, whatever it is, we're adding two vectors here. You always add vectors tip to tail. If I have two vectors, A and B, and I want to know what the sum of the vectors are, I have to arrange them tip to tail, always. So A, I draw as is. And onto the tip of A, I attach the tail of B with the same length in the same direction. And at this point, we define the sum of the vectors, or the resultant. The resultant, you always draw from the tail of the first vector to the tip of the final vector. So that's A plus B. Again, it's known as the sum, the net, the resultant, whatever you want to call it. Okay, so in this case, because I have V2 and I have negative V1 and I'm adding them together because of this expression, my sum, the total vector here, which will represent delta V, goes from the tail of the first vector to the tip of the final vector. Okay? And there it is. You can see it with the black arrow. And where is the black arrow pointing? Towards the middle of the circular path. And this will be true regardless of any 2 points that you pick. You're always going to find that the velocity vector points toward the center of the circle. Okay? Hence, that's the direction of delta V. Now, if you have a vector equation, usually the direction of that vector is given by a vector quantity on the other side of the formula. Not always. For example, with magnetism, we used right-hand rule, but usually that's the case. Right? With Newton's second law, the direction of net force is the direction of acceleration. With momentum, the direction of the momentum is given by the direction of the velocity. So it comes up quite a bit in physics. The direction of acceleration is given by the direction of delta V, which is why if delta V is center pointing, acceleration is also center pointing. Okay? Now the slides note here, you have to be able to sketch this. So make sure you're able to reproduce this derivation and be able to explain it. That's a necessary requirement of this course. The last bullet point on this slide simply says the word centripetal means center seeking. So when you're moving in a circular path, for whatever reason, if you're in a car and you're entering the highway and the ramp to the highway is circular, the car is always seeking the center of the circle. You keep changing your direction. Okay, this is the only reason you're able to turn in a circular path. Okay, so just keep that in the back of your head. Something else to watch out for, a lot of students will confuse these two terms, centripetal and centrifugal. What we are using here throughout our entire course, we are using centripetal force. This is a center pointing net force and centripetal acceleration. We are not dealing with centrifugal force. If you ever hear the expression centrifugal force, it is not a real force. It's not to say that it is made up. Centrifugal force is an imaginary force that we can use to explain things that we observe that we can't necessarily explain in the moment. For example, let's go back to the idea of being in a car. You're entering the highway, you're going around that circular ramp. What happens? No matter where you are in the car, you will always feel yourself thrusted against the wall of the car. So if I'm taking a turn and I'm going towards the right or I'm going clockwise, I will feel my left arm pressing against the door. Right? And if that turn is tighter, if I'm going at higher speed, that force increases. Right? So you might think to yourself, well, there's some kind of a force pushing me to the outside of the car so that now the door of the car pushes on me and I push on it. That's not the case. There's no force pushing you to the door. That's what they call centrifugal force. It appears like there's a force, but there isn't actually a force. The reason you feel pushed against the wall of the door is because of Newton's first law. Objects in motion want to keep moving the way they are unless acted upon by an external force. So when you're moving in a circle, you're going in a certain direction, but the problem is you keep changing that direction, right? The velocity, and which is the same direction as the displacement, it's always tangent to the circle. So if you keep changing your direction, the car's door keeps catching up with the direction that you're moving at that instant, which is why you feel that push, okay? So in summary, centrifugal is an imaginary force. We are not dealing with that, although it's good to know what it is. We are dealing with centripetal force, which is a circular net force. Okay, now we saw this in the last unit, so I won't spend too much time on this. As I keep saying, centripetal force is a net force. From Newton's second law, we know that net force is given by the product of mass and acceleration. So therefore, it would make sense that centripetal force, we can just call it Fc, is equal to the product of mass and centripetal acceleration. Okay? The animation at the bottom of this slide is simply there to show us what we already kind of talked about. The idea that if you're in a car and you're going around a turn, you're going to feel your arm pressed against the door. Okay, so whatever direction you're turning, you always feel pushed against the outside of the circle. Okay, so if you've ever been in an amusement park and you've been on a ride that takes you around in a circle, you probably feel pushed against the edge of that ride toward the outside of the circular path. Again, we call that centrifugal force, but it's not a real force. Right, so that's just Newton's first law in action. Okay. Now, the last two bullet points on this slide simply point out something that I mentioned earlier. So you feel that force from the car door on your arm as you're making the turn. How do you make that force bigger? Well, if you take a tighter turn, well, the door of the car is going to catch up to you much faster. So you will feel a bigger force like that. If you make the turn faster, you will feel pushed against the door even more. Hopefully that's something that you can imagine in your heads. You've probably been in that scenario. If you haven't, next time you enter the highway, whether you're a passenger or you're the driver, pay attention to what's happening to your body and what forces you experience. Okay? Small radius, big centripetal force, big velocity, also big centripetal force. So what we're trying to do here is understand what variables are relating to the centripetal force. Okay? Okay. On this slide, we're going to look at two scenarios, scenario A and scenario B. Okay, so we've got two cars in scenario A, and then we have another car in scenario B. So what we have to do here is identify what the control variable is, independent and dependent variables. So I've got a diagram that involves centripetal force, speed, centripetal acceleration, and distance from the center of the circular path. What I notice in the first case is that the distance from the center of the circular path to the car, that's constant. R is constant, that's the control. Now, what's the person changing? Well, looking at this from far, I can see that the velocity vector has gotten bigger. So they're going around the turn a little bit faster. Now, we just talked about this on the previous slide. If you take the turn faster, you will experience a bigger force of the door on your arm, a bigger centripetal force. Now, if the centripetal force increases, and due to Newton's second law, that's equal to mass times acceleration, well, your mass is not changing. That means your acceleration also had to increase. Okay? In scenario B, okay, let's take a look. This time it looks like velocity is remaining the same. The length of the arrow hasn't changed. But what I notice is that originally I had a certain distance to the center of the circle, and that distance has decreased. So I'm taking a tighter turn. Again, what we saw on the previous slide. If you take a tighter turn, you're going to experience more centripetal force. Okay? So that's why Fc increases, and that's why AC increases. If you're not feeling this, you have to put yourself in this scenario so that you can actually almost hold on to that feeling. When you're taking a turn on the highway, how does it feel? Or maybe you're even on the road. It's not so much of an effect when you're at a red light and you're turning right or you're turning left, but when you enter the highway, you're supposed to accelerate and merge with the speed of the traffic that's on the highway. So the fact that you're actually traveling at a certain speed, at a high speed, much higher than if you were taking a right turn at a red light, you'll actually experience that. And this will help you remember what's actually taking place. Now, all of those changes in the variables I discussed, they're here on the slides. So I will leave the slides up for a second if you want to pause the video and copy down the notes. Okay? Otherwise, we're going to keep on going. By the way, this slide is not in your notes. I just made a note here. This slide and the next slide are actually not in your slides. So if you want, you can always take a screenshot of this after the notes are done, as usual, as I would have done in class. I will post the 6.1 slides so you can see them. Okay. Now, we noticed a couple things so far. We noticed that when your speed increases, the centripetal acceleration increases. We noticed that if you tighten the circular path, you also increase the centripetal acceleration. Or said another way, if you increase the distance, then you decrease the centripetal acceleration. So, notice it says first guess formula. Now, I guess we're cheating a little bit here because you've already seen the formula back in the last unit, and we had to have seen it, otherwise we wouldn't have been able to analyze the circular motion of charged particles in a magnetic field. But just go with this for a second. Your first guess formula is this. You know that the centripetal acceleration is directly proportional to the speed in the sense that if the speed is increasing, your centripetal acceleration is increasing, and you know that the opposite is true for the distance. Right, so if r gets bigger, this should get smaller. So it's not a bad first guess, okay? So in order to understand whether or not that is actually the correct formula, you can use something called dimensional analysis. And if you remember, dimensional analysis is when you look at the units on one side of the formula, you look at the units on the other side of the formula, and you make sure that they match. Okay, for example, here, velocity. This is measured in meters per second. Time is measured in seconds. Meters per second is meters per second squared. Or the new way in which we're writing it, m times s to the minus 2. That's the unit for acceleration, so we know that formula makes sense. Okay, so now we're going to use dimensional analysis on that first guess formula. Okay, now speed. Speed is measured in meters per second. R is measured in meters. But acceleration is measured in meters per second squared. So let's see what's happening with these formulas, with these units. Meters per second divided by meters, you're not even getting anything close. You actually end up with 1 over seconds. If you remember, 1 over seconds, that's a hertz. Okay, so acceleration is not measured in hertz, that's frequency. But we can fix this. If you square the numerator and you square the speed, we actually end up with the correct units. Okay, so now we need meters per second squared, like before. In the numerator, now we have meters squared per second squared. You divide that by meters. You have 1 meter canceling from the top and the bottom, leaving you with meters per second squared. Okay? This is also not on your slides, so just keep that in mind. Okay, next slide. So we've seen the formula for centripetal acceleration, v squared over r, right? And you know that due to Newton's second law, the centripetal force is given by the product of mass and acceleration, which is centripetal. Okay, so let's do some problems. All right, a 730 kilogram smart car negotiates a 30-meter radius turn at 25 meters per second. What is its centripetal acceleration and force? And then what force is causing this acceleration? So this is just an example to get our hands wet. All right, so just to see how to use these formulas. All right, so we have a 730 kilogram smart car. That's the mass. All right, 730. The turn has a radius of 30 meters, so that's r. Remember, the fact that there's a decimal there means we have 2 sig figs in our value for r. If that decimal was not there, that means it would only be 1 sig fig. And the turn is negotiated at 25 meters per second. That's the speed. All right, what what is its centripetal acceleration and force? All right, not too bad. The formulas are at the top of the page. And like I say, keep referring back to your data booklets. Make sure that you know where to find the formulas, where to find constants if necessary. The constants are not so important in this topic. They were in the last topic and they will be in future topics. You gotta know how to look up stuff in this booklet. All right, so looking in 6.1, I have, well, the first formula we haven't covered yet, but we will. The next one is A is equal to V squared over R. There's another formula next to it, which we'll go over. And underneath that, we have F is equal to mv squared over R. That's just F equals ma. If A is V squared over R, well, you see where I'm going with that. Okay. Centripetal acceleration is a V squared divided by R. The V is 25. Everything's an SI unit, so I can go ahead and plug it into my formula. 25 squared divided by 30. I'll give you a moment to get your calculator. Pause the video if you need to. Okay, so if we actually calculate this, we're going to end up getting, well, let's take a look. 21 meters per second squared. Now notice the answer is 2 sig figs, right? So originally we have 2 sig figs in our mass, that 0 doesn't count. 2 sig figs in our radius, this 0 does count because there's a decimal. 2 sig figs in our velocity, that one's pretty easy. Therefore, our answer is to the least number of sig figs, and they're all to 2 sig figs, so we're good. Okay, so that's centripetal acceleration. Now, centripetal acceleration, the direction, this will be the easy part. The direction is always, always, always towards the center of the circle. And the same is for centripetal force. It's in the name, centripetal. Remember, centripetal means center pointing. Okay, so if you want to put a direction in square brackets, you say towards the center of the circular path. Direction, always put in square brackets, and always put a box around your answer. Okay, done. Next, find the force, the centripetal force. Use Newton's second law. Newton's second law says F equals ma. That's F net. In this case, we have a circular net force, so Fc equals mac. In your data booklet, none of the F's or A's, even in that section, they don't have the letter C. You have to remember yourself that those are centripetal accelerations and forces. So do not just use formulas in this booklet because the letter that appears in that formula is the same as a letter that you're looking for. Okay, so sometimes letters can be duplicated, they can be used in different scenarios. It's usually not the case, although that can happen. But you don't want to figure out that you calculated for an electric force and then plug it in here as a, well, as a centripetal force if it doesn't apply. And the only scenario I can see that applying is when you have an electron orbiting around, let's say, a proton. So for example, the hydrogen atom. All right, here we go. So mass, I know, is 730. Acceleration is here, 21 meters per second squared. All right, just have to multiply those two numbers out. Easy. Okay, so we're going to get 15,000 newtons. In the slides, the newtons sometimes have lowercase n, sometimes they're capital N. Usually we want to stick with capital N. With IB, they go back and forth between lowercase n and capital N. With Ministry of Ontario, you have to use capital N. It doesn't really matter in this case because N is not really the unit for anything else. So it's not as if there's going to be confusion there. What force is causing this acceleration? Well, if you're taking a turn, that's got to be static friction. So if you have a car, and this car is going around a turn, so this car is going clockwise, all right, around this turn. it's traveling like this. Now, because the tires are moving against the pavement or the concrete, there's going to be kinetic friction, opposite the direction of the velocity. So that will be opposite the velocity, also tangent to the circle, and it's going to keep changing direction as the car changes direction. But the reason the car can take the turn is not because of kinetic friction, or dynamic friction as IB would call it. It takes the turn because there is grip. When you don't have grip, if you're driving in the winter, or if it's icy on the road, or if it has rained and it's wet, there is poor contact between your tires and the road. So the coefficient of friction has decreased, you have to take the turn slower. That is because of static friction. Okay, so that is the friction between your tires and the road that points toward the center of the circle. So F, F, S. Static friction is what helps you take the turn. All right? All right, moving on to the next slide. Period and frequency. When we studied waves at the beginning of this course, we talked about these two quantities quite a bit. Period and frequency. They always go together. Okay? Frequency is lowercase f, period is capital T. Now, we've already seen the definition for period, but here it is again. The time it takes for an object to complete one cycle or one revolution. Okay, so we're going to be dealing with revolutions here. Frequency. Frequency, well, not only is it the reciprocal of period, frequency is, well, how many revolutions per second do you have? So if you're driving in your car, you've got your dash in front of you, and that dash, that instrument cluster, it's got a lot of different dials on it, a lot of different gauges. You've got the speedometer, it tells you your speed. You've got your gas tank indicator, you've got your temperature indicator, and usually there's one more indicator, and that's your RPM. Okay, revolutions per minute. Okay, that's telling you how fast the engine is rotating. All right. Now, because we're dealing with SI units here in physics, period would be measured in seconds, and frequency, since it's the reciprocal of period, it would be measured in 1/seconds. And we've seen this before, it's nothing new. Okay, 1/seconds is hertz. We actually talked about this earlier in the video. Okay, so how many revolutions occur per second? Period is seconds per revolution. Okay, and we saw this relationship as well. F is equal to 1/T, T is equal to 1/F. If you'd like, pause the video and just refamiliarize yourself with where that is inside the data booklet. Okay, let's try this example. Find the period and the frequency of a day. So you have no numbers given to you in that problem, which means you have to use a very good educated value as you're doing this. Okay, find the period and the frequency of one day. The period of one day is the time it takes for a day. Now, it takes 24 hours for a day. That's common knowledge. What you have to do is just convert that to seconds. So we have 24 hours. Anytime you want to convert units, you multiply by 1. Because this way you're not changing the value in the question, but you just have to choose your 1 carefully. Now, in this case, I might have to multiply by 1 more than once. Because changing directly from hours to seconds, it's not that bad unless you have that number memorized. But if you're, for example, going from years to seconds, you're going to have to multiply by 1 a couple times. Do a couple of unit conversions till you figure out how many seconds are in a year. Okay, so I multiply by 1. And I choose my 1 very carefully. Always replace your 1 with an empty fraction. I'm trying to get rid of the unit of hours, so I stick hours on the bottom, okay? 1 hour. Now, if I know how many seconds are in an hour, I stick that on top. Let's say you don't know. But you know how many minutes there are in an hour? There are 60 minutes. So I fill that in on top. Not bad. I'm going to get rid of the unit for our hours, but I'm stuck with minutes. So I multiply by one more time. So another empty fraction. This time, I'm trying to eliminate the unit of minutes. Since it's in the numerator here, I put it in the denominator in the last fraction. Now, 1 minute has 60 seconds. Right? So this is how you get rid of the unit for minutes, you got rid of the unit for hours, and you're left with seconds. So what we have to do is have 24 times 60 times 60, okay? Whatever that's going to equal. So let me actually grab my calculator here. 24 times 60 times 60, 86,400. So there are 86,400 seconds in a day. Okay. Period. Done. Once you have period, you can find frequency, or vice versa. A frequency is the reciprocal of period. F is 1 over t. So you have 1 over 86,400. Don't leave it like this. Always just figure out what the decimal is. In math, usually exact answers are preferred. In physics, decimals are more than welcome. And for this question, we don't really need to concern ourselves with sig figs because we weren't given any data in the question. But what you need to do is just give your answer to a reasonable number of decimal places. Okay, so 1 divided by 86,400, I'm going to give my answer to 2 decimal places, given that I'm answering in scientific notation. So 1.16 times 10 to the minus 5 seconds to the minus 1, right? Since this is seconds. We don't leave it like that. We always change seconds to the minus 1 into hertz. So 1.16 times 10 to the minus 5 hertz. All right. Okay. Now in your data booklet, 6.1, circular motion, we went through quite a bit of the formulas, but there are still some that we haven't covered yet. For example, the first one, V is equal to something that looks like a W times R. Talk about what that is. The next line, A is equal to V squared over R. We did that, but we didn't figure out what the formula next to it represents or how it comes about. So this is where you're going to see where that formula comes about. And in fact, I'm surprised it's actually in the data booklet because this is a formula that can be derived fairly quickly. But nonetheless, it's there, and I'm going to show you how to derive it. So, starting with the expression for centripetal acceleration. AC is equal to V squared over